Okay, so we learned a little bit about networks, but let's talk about how data is then transferred throughout the networks by talking about packets, deliveries, and protocol. Okay, so in the old days, we used to send letters, right? And you'd write your letter, you put it in an envelope, and then you put an address on the outside. You have a to address and a from address. Well, that's very similar to how we send messages over the internet. There's a to IP address and there's a from IP address. And that kind of tells us how the letter should go, how the data should be transferred. Okay, and here's an illustration about how digital packets are sent through the internet. Now you could see that there's a number of packets being sent because we're not sending one item. Data over the internet is broken up into small packets, small little pieces of data. They're transferred through the internet. They take different paths to get there. But when they all reach their destination, then they're reassembled into the original piece of data. And this is more like a set of postcards, right? You're just writing little short notes on each postcard and sending them off. They could arrive out of order. They can arrive all together. They can, maybe one gets lost. And if one gets lost, you get a message back saying, hey, I lost postcard number 4. Can you please resend it? And then you just send that piece of the message back. So what protocols are then are the rules that govern how this data is transferred. The most common protocol that we use is TCP/IP. So it's the TCP protocol over IP addresses, right? And there's a whole bunch of rules that govern how that works, but the main thing is it works. Okay, and many protocols are associated with a specific port. So if you go to a web page, you're probably using port 80, HTTP. Or if you're sending an email, you're probably using port 25 over the protocol SMTP. The SMTP protocol explains to the computer how to send that message. Okay, and the ports could be physical, like you have on your computer, or they could be virtual. But they are a whole set of well-known ports. And why do we talk about this? Because in security, you need to know what ports, because when you see certain ports being used, you'll know what protocol, and that'll help you determine what the original messages are, right? So if you see port 20, you know that's FTP. And if you see port 22, you know that's SSH. And so on and so on. Then you also might see some weird things happening over port 53. 53 is supposed to be DNS, right? So DNS is the service that connects domain names like code.org with an IP address like 17.21.45.2. But when you start seeing strange traffic over port 53, then you know that something is wrong, and port 53 is being used for malicious purposes. So it's good to know the protocols and the ports, and the more knowledge you have in this area, the more effective you are in security. So let's talk a little bit about a couple of these very famous protocols, TCP and UDP. So for TCP, this is the transmission control protocol, and it's very reliable. So if you lose a packet of data, well, it keeps track of that and it's able to send you that packet again. So anything, any service or program that you want integrity of data, what you send has to be the same thing that's received, right? Integrity. You're going to want to use TCP. So when you send an email, do you want the email to be perfectly exactly like you sent it, or do you want it to have errors? Of course, you want it to be exactly as you had sent it. Right, so how do we ensure this delivery? Well, TCP always makes a connection before sending data. So it does what's called a three-way handshake. So it tries to synchronize a SYN packet is sent, a SYN ACK, a SYN acknowledgement packet is sent back to the computer, and then the original computer then sends an acknowledged packet, and that establishes the connection, and now more data is transferred. So that's pretty cool, because when you know this handshake has occurred, you can trust that connection. And that's all part of this TCP protocol. Okay. On the other hand, we have UDP. UDP is connectionless. So it's much faster than TCP, but it's unreliable. So sometimes packets get dropped or lost and never arrive. Packets arrive out of order and they're useless if they're out of order. Okay, and you might think, well, why would we ever use something like that? We use it every day. When you stream music, when you play video games online, when you're in a video conference, when you watch a video, you don't care if all 5 billion packets arrived and all 5 billion packets were perfect. If you got 0.0009% of all those packets, you couldn't tell the difference. Right? And so more and more, we're moving to a world where we want to use UDP more than TCP. And we're finding new ways to do that. So maybe one day we'll get to talk about that. Okay, let's wrap this all up. So what do we talk about? We talked about MAC addresses, which are the physical addresses of each computer or device. That MAC address is then given an IP address, which allows it to talk within a network, but also allows it to talk over the internet. And how we talk is with different languages, or we call them protocols. And each protocol has a port number, and it uses a method of delivery, either TCP or UDP. Okay, so let me just wrap this up with this quick video from code.org. It's a very good overview of everything we just talked about. And before I do that, I'm going to stop sharing. I need to make sure I am sharing the sound when I share this video. Okay.
7, 6, 5, 4, 3, 2, 1.
Hi, my name is Lynn Root. I am a software engineer here at Spotify, and I'll be the first to admit that I often take for granted the reliability of the internet. The sheer amount of information zooming around the internet is astonishing. But how is it possible for every piece of data to be delivered to you reliably? Say you want to play a song from Spotify. It seems like your computer connects directly to Spotify's servers, and Spotify sends you a song on a direct, dedicated line. But actually, that's not how the internet works. If the internet were made of direct, dedicated connections, it would be impossible to keep things working as millions of users join, especially since there is no guarantee that every wire in a computer is working all the time. Instead, data travels on the internet in a much less direct fashion.
Many, many years ago, in the early 1970s, my partner Bob Kahn and I began working on the design of what we now call the internet. Bob and I had the responsibility and the opportunity to design the internet's protocols and its architecture. So we persisted in participating in the internet's growth and evolution for all of this time up to and including the present. The way information gets transferred from one computer to another is pretty interesting. It need not follow a fixed path. In fact, your path may change in the midst of a computer-to-computer conversation. Information on the internet goes from one computer to another in what we call a packet of information. And a packet travels from one place to another on the internet a lot like how you might get from one place to another in a car. Depending on traffic congestion or road conditions, you might choose or be forced to take a different route to get to the same place each time you travel. And just as you can transport all sorts of stuff inside a car, many kinds of digital information can be sent with IP packets, but there are some limits. What if, for example, you need to move a space shuttle from where it was built to where it will be launched? The shuttle won't fit in one truck, so it needs to be broken down into pieces, transported using a fleet of trucks. They could all take different routes and might get to the destination at different times, but once all the pieces are there, you can reassemble the pieces into the complete shuttle and it'll be ready for launch. On the internet, the details work similarly. If you have a very large image that you want to send to a friend or upload to a website, that image might be made up of tens of millions of bits or ones and zeros, too many to send along in one packet. Since it's data on a computer, the computer sending the image can quickly break it into hundreds or even thousands of smaller parts called packets. Unlike cars or trucks, these packets don't have drivers and they don't choose their route. Each packet has the internet address of where it came from and where it's going. Special computers on the internet called routers act like traffic managers to keep the packets moving through the networks smoothly. If one route is congested, individual packets may travel different routes through the internet, and they may arrive at the destination at slightly different times or even out of order.
So let's talk about how this works. As part of the internet protocol, every router keeps track of multiple paths for sending packets, and it chooses the cheapest available path for each piece of data based on destination IP address for the packet. Cheapest in this case doesn't mean cost, but time and non-technical factors such as politics and relationships between companies. Often the best route for data to travel isn't necessarily the most direct. Having options for paths makes the network fault tolerant, which means the network can keep sending packets even if something goes horribly wrong. This is the basis for a key principle of the internet, reliability. Now, what if you want to request some data and not everything is delivered? Say you want to listen to a song. How can you be 100% sure all the data will be delivered so the song plays perfectly? Introducing your new best friend TCP, Transmission Control Protocol. TCP manages the sending and receiving of all your data as packets. Think of it like a guaranteed mail service. When you request a song on your device, Spotify sends a song broken up into many packets. When your packets arrive, TCP does a full inventory and sends back acknowledgments of each packet received. If all packets are there, TCP signs for your delivery and you're done. If TCP finds some packets are missing, it won't sign. Otherwise, your song wouldn't sound as good, or portions of the song could be missing. For each missing or incomplete packet, Spotify will resend them. Once TCP verifies the delivery of many packets for that one song request, your song will start to play. What's great about the TCP and router systems is they're scalable. They can work with 8 devices or 8 billion devices. In fact, because of these principles of fault tolerance and redundancy, the more routers we add, the more reliable the internet becomes. What's also great is we can grow and scale the internet without interrupting service for anybody using it.
The internet is made of hundreds of thousands of networks and billions of computers and devices connected physically. These different systems that make up the internet connect to each other, communicate with each other, and work together because of agreed upon standards for how data is sent around on the internet. Computing devices, or routers along the internet, help all the packets make their way to the destination, where they're reassembled if necessary in order. This happens billions of times a day, whether you and others are sending an email, visiting a web page, doing a video chat, using a mobile app, or when sensors or devices on the internet talk to each other.
Okay, so that's just a little picture of how it all works. I'll catch you in the next video.